Jai Hind one and all, welcome back for lecture series Engineering Physics. Now, in today's lecture, we'll start our first topic, and that is Gauss Divergence theorem. So what is Gauss Divergence theorem is? It says that the surface integral of a vector to a closed surface area is equal to volume integral of a divergence of the same vector over the volume enclosed by that surface. So if we talk about this, then it says a closed integral of A dot ds, where A is a vector, ds is a closed surface, is equal to complete integral del dot A into ds. That means if you take a dot product of a del with a particular vector, then it can be a divergence theorem. Now, if you talk about Gauss theorem, line integral of a vector over a closed loop is equal to surface integral of a curl of the same vector over the surface area enclosed by that loop. That means this is based on dot product and this is based upon cross product. This is based upon cross product. So if you take a dot product of a del with some vector, then it's a divergence, and if you take a cross product of that particular del operator with any vector, then it will be a curl or a Stokes. We use them when we are going to convert one form to another. Here if you see that closed integral of a surface gets converted into volume, just multiplying a del operator with that particular vector. Now in the next one, if you multiply this particular vector with a del, then if we take a cross product of it, then your dl gets converted into ds. So here the transform is from ds to dv, and here it is from dl to ds. It is very easy to understand. Now, Ampere's circuital law, we all learn about it. Now, what it says, the line integral of a magnetic induction vector around a closed path is equal to mu times of a net current crossing the area enclosed by that path. And we understand that if we have a particular, we have a loop, we have a current going here, and now if I take a distance r from here and take a small surface as dl over here, and this is magnetic field over here, then I can say that closed integral of a B, and B is a magnetic field, into dl. dl is the length of this wire, is equal to mu times of the current. And we have used it many times when we are doing our 12. So this says the closed integral of B dot dl is equal to mu naught n I, where n is number of turns in a coil. So from here we understand that, we also know that current can be written in the form of I is equal to integration J dot ds. And what is J over here? J is a current density. This is a current density. This is a current density. So current can be written like this: I is equal to J dot ds, and now that J dot ds can be replaced by that I, and in place of this I we can use J dot ds. So we'll get a complete value as V dot dl is equal to mu naught integration J dot ds. So what is J? J is, if you want to recall, J is a current density, number of current lines moving cross sectional area. This is our J. Okay. So where J is the current density, they have written over here also. Now we will learn about a very important topic, and that is equation of continuity. Equation of continuity. We have learned from Bernoulli's theorem. Bernoulli's theorem is based on the equation of continuity, and it says that equation of continuity. We can recall it. There is a two column. It has a cross-sectional area A1. This is a cross-sectional area A2 with a velocity V1, and this is a velocity V2. And we say that my AB is a constant. You might have recalled it from the previous knowledge. And AB is a constant. That means the amount of area we have here depends upon the velocity, and over here also, if we squeeze our area, then my velocity will get increased. We have done it previously in our houses also. You take a pipe, water pipe, and just take your thumb and put it on the mouth of a pipe. What will happen? The cross-section area will get minimized and your velocity get increased. So here you can see from here this equation also, that A1 V1 is equal to A2 V2, and clearly we can say that my A1 upon A2 is equal to V2 upon V1, which says that my area is inversely proportional to the velocity. If you increase the area, then velocity get decrease, and if you decrease the area, then your velocity get increase. So this is the phenomenon. Okay. So this is the concept of equation of continuity, and we know that I is equal to integration of J dot ds in generalized form. If area is enclosed, that integration get converted into a closed integration, and we will write it as closed integral. So you can see from me, I will get equal to closed integral of J dot ds. Now consider a closed surface S enclosing a volume V. Suppose a closing surface S enclosing a volume V. If rho is the volume density inside the volume, we have learned this in the previous class. What is linear density, what is area surface density, what is volume density. So we have learned this. So we know that my I is nothing, my current can be written as dq by dt, and we have put a negative sign here. Here negative sign indicates that the charge decreases inside the volume with time. So charge will get decreased in a volume. If you put a charge inside a volume, you will get to know that after some time that whole charge will come on the surface. That whole charge comes on the surface, and that's why we are saying that charge inside a volume gets decreased with time, and because of that we have used that I can be written as I is equal to minus dq by dt. Again, what we can do is we will differentiate it, and I can be written as minus dq by dt, and why we have written as, I'll tell you. Okay. From our previous knowledge, we know my rho is nothing but charge by volume. But if we talk about a small volume, we can write it as rho is equal to dq by d. And in place of dq, we can write from here, we can write dq is nothing but rho into dv, and you can see over here. You can see over here that my I gets converted into minus d by dt. Put that d by dt outside, integration rho dv. Rho dv. So this is my second equation. This is my first equation and this is my second equation. If there is neither a source or a sink inside the volume, then according to law of conservation of charge, what is law of conservation of charge? Charge cannot be created nor destroyed, can be converted in one form to another, or it can get transferred from one place to another, is the concept of conservation of charge. So neither a source nor a sink. That means there is no source which is producing the charge and there is no source which is destroying the charge. Then what will happen? What will happen from here? I is equal to closed integral of j dot ds and I is equal to minus d by dt integration rho dot dv. That means from 1 and 2 what we will deduce is both the equation are same, because we don't have any source and we don't have any sink over here. No, what will say? My closed integral j dot ds will get is equal to minus d by dt rho dv. And now we will use the concept of divergence over here. How? We get this equation. We get this equation, and clearly I said that when we are converting or going from ds to dv, we use divergence. So you can see here my ds and my dv. So we are getting converted from ds to dv. And what is the formula? What is the formula? Formula is just multiply, take a dot product of del with that particular vector. So over here, close j dot ds. What we have learned? We have learned close a dot ds is equal to complete vector del dot a into b. We have learned this. So we will apply Gauss Divergence theorem on the left side. Just apply it on the left side. So what will you get? We have close integral j dot ds, we have close a dot ds, see, and we can replace this value with this. We can replace this value with this, and this is what? Complete vector delta dot j dot d. So we can write over here. See what we have written? We have written that my integral, my this part gets converted into this, and we can write it as integration del dot j into dv is equal to minus d by dt rho dv. And why we have done it? We have put dv on both sides so that the calculation can be very easy. So what we will do? See, del dot j dv. So we'll take all the thing. We will take all the thing one side. We will take all the thing one side, and what we'll get is this minus get converted into plus, and we'll take dv outside and integration outside, because we have integration, we have dv and dv, so we can take them out and integration, and what we left with del dot j plus curl d rho by curl dt into dv is equal to 0, and the integral must be 0 for arbitrary action. Okay, so what will happen? What we have learned? We have learned that if x dot y is equal to 0, that means here either my x is 0 or my y is 0. So here we can say integration del dot j dot dv is equal to 0, and they have written that the volume cannot be nullified. Volume will always be there. So what will get nullified is integration part, and we can say that del dot j plus curly rho by curly t gets converted into 0, and this is the equation of continuity in the form of conservation of charge. It states that total current flowing out of the sum volume must be equal to rate of decrease of charge within the volume, assuming that charge can neither be created nor destroyed. So for a steady state means nothing is moving. We can take differentiation, change. There is a change. If we are talking about steady state, that means nothing is changing. But according to this equation, something is changing, and that is rho. And because it is saying curly rho by curly t, or we can say there is a change in rho by change in time. So for the steady state, we can say curly rho by curly t is equal to 0, and we are left with del dot j is equal to 0. So this is our final equation. This is our final equation, and in special case we can use del dot j is equal to 0. Now, the one more important term comes in our mind when we are talking about electromagnetic theory, and that is displacement current. So what do you mean by displacement current? Okay, the concept of displacement current was first introduced by Maxwell purely on theoretical ground. The displacement current does not have significance like the current in which the charge actually moves. To demonstrate the displacement current, consider an electrical circuit in which a capacitor is charged with a battery. So what he observed is, I'll tell you. So he says that if we have a capacitor is a device which can store charge, right? Yes. And now if we apply a battery over here, plus and minus, what we will observe? We will observe that this particular part become plus and this particular part become minus. But there is a gap between them. And what he observed is there is a current in between them, and that current is called displacement current. So why it can happen? With the previous knowledge of electric field, what we can understand is from plus to minus we have one thing, and that is the electric field. And if there is an electric field, then there must be a force, and that force is equal to 2 into E. We have learned it. Since we have a charge, we have a, and this is a, and if we differentiate Q with time, then it is a current, and that means he's observed something in between here, and that thing is nothing but a displacement current. Okay, so what he did, he has taken one apparatus, he has taken one capacitor over here, and taken one surface over here, a cylindrical surface. What he did is, he taken a capacitor and he has taken a semi-sphere part over here. He called it S1 and he called it S2. This part as S2. He connected it with a resistance and then with a battery. And now what he will do, he will charge and discharge, and because of that he will understand the concept of displacement current. Now consider two surfaces, S1 plane, S1 is plane, this is a plane surface, and S2 is a hemispherical. He has written inversely, this is a hemispherical and this is a plane, bounded by a common closed path. Why? If the current I come from here, it will move to this part also and this part also. That's why he is saying it's bounded by a closed common path. Like at any instant of time t, the current is I. Apply a law. Okay. Now, see. Now what we have to do? We have to apply Ampere's circuital law at this particular point, and we have to apply same law at S2. So what we will observe? Here we have a hemispheral layer. So what will be the answer? Then my answer will be applying Ampere's circuital law at S1 will give me closed integral B dot dl is equal to mu naught I at this particular point, because current is actually moving through it. But what about inside a capacitor? We have learned in 12 that inside a capacitor, inside a surface, inside a volume, my current is 0. So we can write applying law of surface S2 is closed integral B dot dl is equal to 0. So at one particular point we are getting mu naught I, and at one particular point we are getting 0. But if you see, the same common current is moving from both of them. So why it has happened? And that is something he observed, and he understand that there is some ambiguity in that law. So he rectified. And how did he do it? Because inside the capacitor dielectric current is 0 and its value is 0. Now we see that equation 1 and 2 are contradictory to each other, which is impossible because one is saying mu naught I and another is saying 0. So Maxwell removed this controversy by adding a new factor, mu naught epsilon naught d phi e by d. So what he said? He said that instead of B dot dl is equal to mu naught I, I don't agree on that. He said I don't agree on that, and he said if we use another term along with this current, and that is mu naught d flux E by dt, then something can happen. So what he did? He rewrite the equation, and he said mu naught B dot dA is equal to mu naught I plus epsilon naught d phi E by dt. So instead of using current I, he also added something in it, and that is epsilon naught d phi E by dt. And he rewrite it, and he said that this current is my conduction current, and this particular value epsilon naught d phi E by dt is nothing but a displacement current. So he used one more equation, third equation. He provides us third equation, and now the displacement current is equal to conduction current in Now he is going to prove it. Now he wants to prove it that what he is saying is the correct thing. So what he did, he said let an instant of time charge on the capacitor is q. So he said at one particular point, capacitor is charged with q, and he knows that electric field, because one is plus, one is minus, then electric field move like this. So he knows that my E is nothing but E upon sigma upon epsilon. And what is sigma? Sigma is nothing but Q by A, and this is a surface charge density. So if we combine these two, instead of using sigma, we can use Q by A. I can write it as Q upon epsilon naught A, and this is the equation. So we got fourth equation over there. Okay. Now where A is a surface object. Now if you differentiate this, if you differentiated dE by dt, dE by dt is equal to 1 upon epsilon naught A. Area is constant, surface area is constant for something, and your epsilon is also constant for some medium. So they will come out, and what is there which can change is your charge, and we can say dE by dt is equal to 1 upon epsilon naught A is equal into dQ by dt. And what is dQ by dt? Current. So we write it as I upon epsilon naught A. And take this value over here. You just take this value over here, and we can write it as I is equal to epsilon naught A into dE by dt. dE by dt. And now take this I inside it. What he did? He said I epsilon naught d E A by dt. Okay, so EA, we know that flux is nothing but E into A, so we can write that my epsilon naught dE dot A by dt, and E dot D is nothing but E dot A, so we can write epsilon naught d phi E by dt, and this is nothing but ID. So he has proved this also. So with this we will end this discussion, and in next class we'll take some other topic. Thank you.